Big data is difficult to classify. In this video, we're going to look at an algorithm known as a classifier. And we're also going to see some very important concepts, which I'll point out as we go. So big data with labels means that we're looking at a structured label data set. And that means rows of observations of features and in this case also responses. Our goal is to predict the responses to unlabeled observations. And the prediction problem, therefore, is to use structured labeled data to construct a model, often an algorithm, that best predicts a response given a sample of the features. So given a sample of the features, predict the response. And often the response is a single variable y. Now, let's look at regression versus classification. First off, a variable is random if it is not possible to predict the next sample given the previous ones. A variable is continuous if all possible values of the variable form an open interval in R, or could be all of the real number line. If the response and at least one feature are continuous variables, then prediction is a regression problem. If the response is a single variable y with only finitely many possible values, C1 to CL, these are called labels or classes, then prediction is a classification problem. For example, let's look at some simulated calculus grades. By simulated, I mean they've been anonymized and reformulated so that you can't identify a student from these grades. Calculus students take 4 exams in a final, all out of 100 points. They pass the class, or pass equals 1, if the average of the exams is 70 or better. Otherwise, pass is 0, which corresponds to failing the course. Recall the exam 5 here is the final exam. Previous is 1 if the student had calculus earlier, and maybe in high school, or they're repeating the course, and 0 otherwise. Notice that of these columns, none were said to be features versus responses. That is something we have to figure out as part of our problem-solving process. But an example of a regression problem might be to use previous in exams 1 to 4 to predict the final exam, exam 5. In which case, our feature variables would be x0 to x4, previous in the 4 exams, and our response would be the exam 5 score, the final exam. For example, given some set of numerical values of the x's, can we predict y, the final exam score? A classification problem might be to use previous in the exams to predict pass. This is actually a sort of silly problem because you don't need data science. All you have to do is take the average of the 5 exams, and if it's bigger than 70, pass equals 1. So let's come up with a more interesting question. What if we wanted to predict whether or not a student passes the class before they take the final exam? Well, in that case, exam 5 we wouldn't know before the final exam because it is the final exam. So we would have these columns, and the first previous would be x0 up to x4 for the 4 exams, and our response would be whether or not a student passes or fails. So now let's look at an important concept which we introduce here, and I don't expect you to understand it in detail after this introduction. We'll develop the details as the course progresses. And that is classification as a predictive model. So suppose we have a sample of the features, x1 to xn, which is a set of numbers, lowercase x1 to xn, which satisfy uppercase x sub 1 equals lowercase x sub 1. The uppercase x1 is a variable, the lowercase x sub 1 is some number. And given that, we could ask, well, what is the set of all possible samples of the uppercase x1 to xn, and that's what's known as a feature space. It's often a vector space, Rn, although we often focus on only a subset of Rn. Grades are non-negative, for example. Pixel intensities are between 0 and 1. But given a sample or an observation in our feature space, how could we predict a label for that observation, where the possible labels are C1 up to CL? Well, the way we do it in general is we calculate a probability. So in particular, P sub k is the probability that a given sample, a point in feature space, has label k. Let's introduce some notation. Usually we don't write the word probability, we just write PR in function notation. So that we could equivalently say the probability that y is ck, given that we have this sample of the features. So that means we have a probability distribution for each point in feature space. The highest probability predicts the label if it's sufficiently higher than the other probabilities. For example, digit recognition, each observation in the data is the image of a handwritten digit. There are 10 classes. Given an image, predict which digit it is. So given this image, we might predict that it's a 7. But as a predictive model, how would we do that? Well, we would get a P0, the probability that it's the 0 digit, and maybe that's a probability of 0.01. Similarly, we can calculate, come up with an algorithm that predicts the probability that its class is 1 for that image. And continuing, we do this for all 10 possible digits, 0 up to 9, and it will turn out that the highest probability is the class is 7, given the image is our image. Here it's 0.88, that's the highest by quite a bit, so therefore we predict that digit is a 7. Now in this class, we're going to focus in particular on data with two classes, class 0 or class 1. This is what's known as binary labeled data, also termed positives class 1 or negatives class 0. Now, one of the reasons we do this is that if we want to extend to more than two classes, it's usually very straightforward. And we'll see that when we revisit this digits data example later. And we call a classifier with only two possible classes a binary classifier. And a binary classifier as a predictive model means we want to figure out what is the probability that an unlabeled observation is class 1, or in other words, is positive. And the nice thing is we don't really have to worry about all the classes because the probability that the class is 0 is 1 minus the probability the class is 1. So we have a nice model where we only have to consider one probability calculation at a time. Geometrically, we can visualize a classifier as binary labeled data with only two numerical features as points in 3D. And then given a point, an unlabeled point, we can ask, well, what should I put there, a 0 or a 1? Now, in order to do this, another important concept, which we introduce here, I don't expect you to know it in detail, but we will develop it in detail as the course goes along. So first off, if you have 2 points, then the set of all linear combinations, alpha p plus 1 minus alpha q, where alpha is in 0, 1, forms a line segment. So here's an example. As alpha goes from 0 to 1, we get the line segment. Now, the convex hull of a set is the set of all linear combinations or line segments between points. So it's pretty simple to see that the convex hull of these points is given by this green region. If the convex hulls of the classes of a binary dataset do not intersect, there must be a hyperplane that separates positives from negatives. This is what we call linearly separable. Now, this theorem is from convex optimization, which is a topic in a field called operations research. But notice how useful it is. I have here, pretty obviously, the positives and the negatives can be separated by a line. And a line in 2 dimensions is the hyperplane in 2 dimensions. Notice the convex hulls here are disjoint, and that's what tells us that there must be a separating hyperplane. The margin is the strip parallel to the separating hyperplane between the hulls. A predictive model is a heat map on the plane. So essentially it's a more green if it's high probability of 0 and more black if it's high probability of 1. And so you get something like this. Notice that if you get too far away from the data itself, then we really have no way of knowing if it's class 0 or class 1. And notice here we include our convexity. So we're going to say that data is separable only if it's linearly separable or if you can transform into linearly separable. For example, here I have not linearly separable, and notice that if it's not linearly separable, I can draw an arbitrary shape that separates, and then I could just turn around and draw another arbitrary shape that separates the positives from the negatives. But that's going to give me different predictions for an unlabeled data point. So we don't want to use arbitrary separating curves. We only want to use hyperplanes, or if we can transform the data to where we can separate with hyperplanes. So for example, this data is clearly separable, but not with a straight line. But notice that we could say take log space of this data, logarithms instead of actual x's and y's, and notice now we have separable data. We could define new variables, which allows polynomially separable data to be linearly separable in higher dimensions. So here we have data, and it can be separated by z equals x plus x squared. But if we let y be equal to x squared, then we get z equals x plus y, which is the equation of a plane in 3 dimensions. And that means that we could lift this into a higher dimensional space, in which case we can actually separate it by a plane. This is the hyperplane separation of this transformed data. So if we can transform to get linearly separable, then we can use algorithms for linear separation. But we don't want to allow anything other than linear as a separator. No arbitrary curves. Instead, we use dimensionality. Data that may not be linearly separable in 2 dimensions may be linearly separable in 3 dimensions. Data not linearly separable in m dimensions may be linearly separable in much more than m dimensions. And in fact, maybe it's separable in an infinite dimensional space that contains our original feature space. So for example, the XOR is not linearly separable in 2D. So notice that here we have X and Y, and the class is the truth value. So 1 and 0, the truth value is false, and so therefore you get a 0. And you get the same thing for OR, but then for the XOR, notice that 1 XOR 1 is 0. So the XOR is class 1 only if exactly one of the features is equal to 1. Now the AND is linearly separable. The OR is linearly separable. The XOR, I can't draw a line that separates the ones from the zeros. If I define a new variable, z equals x plus y mod 2 in terms of x and y, then this problem, which there is no line that separates trues from falses, but in a higher dimensional x, y, z setting, let's see what happens. So in this case, notice that I can rotate, and what I'm going to do is rotate and show you in 3 dimensions the effect of the z variable, which is to allow a separating hyperplane. In other words, I can now draw a line, or in this case a hyperplane, a plane between the trues and the falses. Now I need to point out that linear separation may be impossible. The multi-scale nature of big data can make it impossible to linearly separate between classes. So there may be no transformation, or at least not one we'll get in our lifetime, that can separate. Convex hulls may always overlap, intersect. So you've got a point xy in the unit square, and you look at it as x plus iy, a complex number, and then you expand it into a binary expansion. If in the binary expansion the digit 1 occurs with a frequency greater than 0.25, then we call it class 1, otherwise it's class 0. And that's what this data looks like. Another example, suppose you have a point in the plane as class 1 if Newton's method for z to the 4th minus 1 converges to a real root, starting at the initial point z naught equals x plus iy, and is class 0 if it converges to an imaginary root. As you can see in these 2 examples, drawing a line or even imagining a transformation which would take you to a point where all the green would be on one side of some hyperplane and all the black on the other, it's pretty hard to imagine. So, algorithms that learn often do not need separability. Nearest neighbor algorithms are simple, useful, and robust, and the starting point for all learning algorithms. This is a key concept in Module 3. So what is a nearest neighbor classifier? Well, to predict the class of an unlabeled point, in this case red, instead of separating, we simply look at its nearest neighbors that already have labels. And now we can do a weighted voting scheme, perhaps 0.75 confidence that the red point is positive, or we may vote weighted by distance. We could also do regression by taking averages or some other numerical calculation over the values of the neighbors. So nearest neighbors, however, is an embarrassment of riches. They can get out of control. Too few neighbors, you might get bad predictions. Too many neighbors, you can also have problems. We'll use lots of testing and validation when we do nearest neighbor methods. Linear separation, conversely, is based on powerful mathematics, hyperplanes. Convex optimization is foundationally important, but studied in another course. So let me just mention, I don't expect you to know convex optimization. I'll point it out when we brush up against it. But in general, the methods we develop in this class will be built from scratch, with me assuming no background beforehand other than calculus and linear algebra. So classification problems. We have an observation or a sample of the features. That's one of finitely many labels or classes. In other words, class is another name for label and vice versa. We want to identify or predict the class category label of a new observation. A classifier is an algorithm which does this. So given an observation, you get a label. Our focus is going to be on binary labeled data and binary classifiers, where binary means 2 classes, often called positives and negatives.